Hello my dear students, I hope you are doing great. Now I'm going to show you something really important, and it is widely used to find the radius of curvature in the circular motion problem. And now let's see the proof of this radius of curvature. And why I'm showing this proof, because you will see a lot of microscopic analysis which can be relevantly used in so many complex problems. Let's see this proof. So by the way, radius of curvature is defined like this formula: r is equal to 1 plus dy over dx first derivative squared power 3 over 2 upon the second derivative, which is d2y over dx square, and the mod here, mod because the radius of curvature is always positive. And first of all, let's try to understand on microscopic level what is radius of curvature. So let's say that if we have any general curve y as a function of x here, so at this point, what does radius of curvature mean? So here, if you take any point whose coordinate is x comma y, and then you are taking a point very near to this point, such that this arc length is very small. So here you can see that if this is very small, then this can be the part of the big circle like this. Okay, so this arc length, this is the arc length which is on the curve, is also situated on this circle, so that this arc length is very small. Let's say that this arc length is ds, which is also the elementary length of this curve, okay, at this point. And this point we have the coordinate as x plus dx comma y plus dy. This is the coordinate of this point. So radius will be basically the radius of the circle, and this is the center of the circle, which is known as the center of curvature. So we have this at this point, we have this radius r. If this angle is d theta, which is very small, this d theta is very small, then we can also write as ds is equal to radius r times d theta in this circle, because this arc length is on the circle as well as on the curve. Okay, now we know that this is the radius of curvature. We have to arrive at this formula. How we can do that? Let's see. First off, what we can do here, we can draw tangent at this point. So tangent at this point is going to be like this, which meets the x-axis here. And let's say this forms some angle. Let's say this forms an angle theta, and I will show you that tangent theta will be same as this small angle. And let's say that we have another tangent here, okay, and this angle will be how much? Let's see. Okay, so this is 90 degree, okay, because this is the normal. And if the tangent turns by some angle, then this normal will be turning by the same angle. So if this angle is theta, this will be theta plus d theta. And also one important thing, I'm putting mod here because theta can be negative as well. If the curve is like this, if the curve is downward, then if you go from here to here, in that case your theta will decrease. You can see that if this angle is theta, then in that case theta will decrease here. That's why I'm putting mod, because ds is the path length, which is always positive. Okay, so now how we can derive? Look at this equation, and also we have the slope of the tangent as tan theta. So slope of this tangent at this point, any point x comma y, is tan theta, and this tan theta is nothing but your dy over dx is the slope of this tangent. So we can differentiate it. Why I'm differentiating? Because you can see in this formula we have something 1 plus dy by dx whole square, 1 plus tan square theta. So if you differentiate it, you will be getting, differentiate with respect to x both sides, then you will be getting sec square theta times d theta over dx is equal to second derivative, which is t2y over dx squared. And sec square theta, by the way, can be written like this, that is your 1 plus tan square theta, sec square 1 plus tan square, which is dy by dx. So I'm writing here as 1 plus dy by dx whole squared times d theta over dx is equal to d2y over dx square. Now you'll be getting, okay, we have this relation d theta over dx, how we can get this d theta over dx. Okay, so in order to get d theta over dx, and using one more relation here, see, this is the arc length, which is very, very small. And by the way, this is your dx, elementary change in x, and this is your dy, and this is your dx. In this right angle triangle, Pythagoras theorem says that this arc length, or this will be nearly straight. So this hypotenuse will be ds is equal to square root of dx square plus dy squared. This is your ds. And by the way, you can take dx out of this square root, then you will be getting dx square root of 1 plus dy over dx whole squared. So this is your ds. Now look at this. We have the equation number 1, and then we have this equation number 2, and then we have this equation number 3, and from these 3 equations we'll be getting the radius of curvature. Okay, so here ds r d theta. So what we can do here, I am putting ds over d theta. Okay, it will be dx over d theta, and we have d theta over dx is this relation. What is ds over d theta? If you see here, ds over d theta is your radius of curvature d theta, then you will be getting ds over d theta, which is r is equal to dx over d theta square root of 1 plus dy over dx whole squared. Okay, and by the way, you will have to put mod here also, because mod of ds over d theta is radius of curvature. So I'm putting mod of dx over d theta. And if you put mod of here, then this becomes mod absolute value here. Then you can plug the value of dx over d theta from equation number 2 in this equation. So finally you will be getting like this, as r is equal to 1 plus dy over dx whole squared, square root of this over mod of d theta over dx. And what is mod of d theta over dx? You can see from equation number 2, you can plug this value down here. So you'll be getting 1 plus dy over dx whole squared, square root of over mod of d theta over dx is mod of d2y over dx square, and this upon 1 plus dy by dx whole square, which will go into numerator, which is 1 plus dy over dx whole squared. And finally you will be getting this result as 1 plus dy over dx whole squared power 3 by 2, this upon mod of d2y over dx square. This is the final result of the radius of curvature. That's the overall explanation for the proof of radius of curvature. So I hope students you got it very well. In case you have any kind of confusion, you can comment below and let me know. Thank you very much students. See you in the next video.